me begin with a word of prayer. So, dearly Father, we thank you for this day. Again, I thank you for these students and this class. Just ask you to bless our work today. Help us to glorify you what we do, and just understand a little bit more about the geometry of curves today. Lord, in your name I pray, Lord Jesus. Amen. Lest I forget, here's the exciting attendance sheet. Here's that. So I hope that the surprise attack mission's graded and I get it back to you tomorrow, hopefully. We'll see. So if you didn't finish it, that's okay. Like, there wasn't quite enough time for it, I think. So I'll probably end up curving it a little bit, but we'll see what happens. I think I only really saw one person who finished the whole thing. I would say if you didn't finish the first page, you might have skill issues, according to my children. Or you really haven't done your homework, right? I mean, because it was homework. So, but if you got the first page, the second page, you've got the first problem done, that's good. If you got past that, you're elite. All right, like, it's not, most people aren't going to get past the first problem on the second page. So I did intend for you guys to have a little bit more time, but then a question was asked which derailed me a second there, and so I did want you to have a few extra more minutes, but anyway, it's okay, we can curve. So today I want to talk about the geometry of curves in 3 dimensions. And so, like, the fundamental question that we're trying to ask and answer is, if you have 2 different curves in 3-dimensional space, when is it possible to take one curve and, like, move it and make it to the other curve, right? Like, so as a kind of very silly example of this idea, I could have these two. This is a very kind of boring example, but it'll serve to illustrate the idea. If I have this line segment, right, and if I have this line segment, these are congruent in the sense of high school geometry, because I can take the red line segment and I can translate it over to here, right? And then I can rotate like this, and voila, they're the same, right? So how would you judge the same for 2 curves? Like, if I have one curve, maybe here, that's like this, whee, right? And I have another curve over here that's like this, whee. Is it possible to translate this over to here and then rotate and have them align directly? Are they congruent in the sense of high school geometry? Well, what I'm about to describe to you will give you some tools that will allow you to actually answer that question directly in terms of calculating certain geometric quantities corresponding to the curve. And the interesting thing is the calculus that we're going to uncover here is also useful for understanding physics and I got no juice. My eraser shirt, it's not here. I feel naked. Let's see here. Oh man, what to do? This is horrible. I will. All right. I have become Sprano. Here we go. So define. So the big concept we need for this class is the concept of a vector field along a curve, right? So, like, I can kind of draw that graphically. If this is a curve, right? If I have at each point I attach a vector, that's a so-called vector field along the curve. And so it's just what it sounds like. You attach a vector. If you can give me a vector at each point along the curve, then F is vector field along C. All right. So what I want to describe to you guys is how we can actually attach a vector field to a given kind of curve in such a way that the calculus of these vector fields that I'm about to describe for you will reveal the shape of the curve. So here we go. Definition. Let gamma from A to B to R3 be a path from P to Q in R3, which is regular. Regular also could mean that just means nonstop. I called it nonstop yesterday. But a regular curve is one for which the velocity is non-zero. All right? And I think this regular term also presumes that the derivative of the path exists. So like we can calculate the derivative at each point in the domain, and it also is non-zero. So it's regular and nonlinear. What does it mean for the path to be nonlinear? It's not a line, right? Pragmatically speaking, what that actually means is this in terms of calculus. It means that d squared gamma dt squared is not equal to 0 for all t. That's the wrong way to say it. Let me say it this way. D squared dt squared is not identically 0. Like if you had the acceleration of the path is 0, we could integrate twice, and what would happen? What happens if, like, let me change notation here for a second. What happens if the position d squared r dt squared is equal to 0? Integrate once, we get dr dt equals to what? Like c1 vector, right? Integrate a second time, we get r of t is equal to t times c1 plus c2, right? That is a line with direction vector c1 and base point c2, right? So we don't want that. We want a path which is nonstop and nonlinear, which is to say that the second derivative is non-zero. Okay? All right, so if you have all that, then number one, the big T. And I said I didn't put a vector on this like yesterday or the other day. I was wrong. I forgot I put vectors on it. I'm sorry, guys. So the T vector of T is 1 over gamma prime of T, the length of that, times gamma prime of T. So this has a name. This is the so-called unit tangent. It's the unit tangent to the curve. Or we might call it the tangent vector field to the curve. So this is T. Number two, we define n of T to be equal to 1 over the length of T prime of T times T prime of T. This is what is known as the unit normal. To gamma. And we don't usually use the word unit. We typically just say normal. This is the tangent field. This is the normal field. All right? And then 3. Last but not, well, I mean, none of these at least. They're all kind of equally important. Big B of T is equal to T of T cross product with, my bad, N of T. T cross N of T. This is known as the binormal. I'll find unit, it's the unit, but no one says unit. It's just the binormal vector field, binormal to the curve. All right. And every one of these is defined for all t going from A to B, right? The domain of the path. notice this construction here. This makes, let me get this right out in front of us. We see TNB is right-handed triple, that is a frame, right, attached to the path in question, attached to gamma. All right. So like if I try to picture it over here for a second, if my path looks like that or whatever, the tangent vector field, you're maybe kind of already initiated into understanding that. I'll use green for that for the moment. It points in the direction in which the path is going, right? So we have to talk about, that might be going like this, all right? There's your t. N, it points in the rate of change of t. Now it turns out, as we study this, that we're going to see that the rate of change of t, it cannot be in the direction of t. The rate of change of t cannot be in the direction of t. We'll derive that soon. And so what that means, it turns out that the n actually has to be perpendicular to t. And so n, it turns out, points like this, basically. Here's your n. It's perpendicular to t, and if you could fit a circle to the curve, it would point towards the center of that so-called osculating circle. The binormal, well, it's the Cartesian product. Listen to me, Cartesian product. What's wrong with me? The cross product of t and n. Okay, so t crossed n, these coming out at us, right? So maybe it looks like that here. Let's see here, t crossed into n. There it's going into the board, right? T crossed n, it's going into the board here. Okay. Let's calculate the TNB frame for a helix. Okay? Yeah.
Would there be a normal vector going from the positive z and negative z in that context? Like you have some that go down from our point of view and then some that go up. Does it matter?
Well, the Frenet normal, as this is called also. This is actually the Frenet normal, truth be told. The Frenet normal points towards the direction of the curve in which you can fit a circle inside. So it's definitely that way, or that way. Because if you look at it, you can kind of see there's a giant circle here, right? That just kisses the curve there. There is another concept of normal we talk about much later in this course, which is the outward pointing normal to a closed curve. And then the normal would be pointing the other way you're thinking about. And yes, in principle, if you have a curve in the plane, there's two different choices for normal, right? Either the Frenet normal or the outward pointing normal if we're talking about like a closed curve. But if we're thinking about 3 dimensions, the choice for a normal to the tangent vector, well, there's infinitely many, aren't there? So the Frenet normal is just one choice of infinitely many. See, because if I am thinking about 3 dimensions, right? If I'm thinking about 3 dimensions, if this is the tangent vector, right? The normal could be any of these guys, right? Any of these guys could be normal. But the Frenet normal is a specific one as defined right here by this equation. All right? Do you see why these are unit vectors? Does that make sense? The definition is what? It's the length of the vector. You're multiplying by 1 over the length of this vector. 1 over the length of that vector. By construction, they're unit vectors. All right. So, example 1. Let's look at that helix we looked at last time. Gamma of t is like r cos t, r sine t, mt, right? we worked out that d gamma dt, also known as gamma prime, was minus r sine t, r cos t, m, right? And so like the length of gamma prime of t, which we also call that the speed, right? The length of gamma prime was the square root of r squared plus m squared. We talked about this last class as well, right? That's the speed, by the way. So what's the unit tangent? So here, unit tangent is simply 1 over the square root of r squared plus m squared. And we've got our minus r sine t, r cos t, m. So there you go. That's the unit tangent field. So what's dt dt? So big T, dt, otherwise known as t prime, right, is, well, let's leave that constant out front, you know. And if we differentiate minus r sine t, we've got minus r cos t. And minus r sine t, right? And the derivative of m, I like this one a lot, 0, right? What's the length of dt dt, or the length of t prime? It is 1 over the square root of r squared plus m squared times the r that you just told me. Because we have a multiple, okay, so when we take a length, right, like the property I'm using for vector length, you write it somewhere. If we have the length of like a constant times a vector, say w, that's equal to the absolute value of the constant times the length of the w vector, right? This is a property of vector length. That's what I'm using in this calculation. It's just that the constant's positive, so the absolute value is kind of irrelevant. So I've got, 1 over the constant times the length of this vector, but that's clearly a vector of length r, because when you calculate the square root of r squared, r cosine squared, r times cosine t squared plus r times sine t squared, you get r. We have to use square root. All right. So what is the normal vector then? Well, the normal vector is apparently, let's see here. The square root of r squared plus m squared divided by r times 1 over the square root of r squared plus m squared times minus r cos t minus r sine t, 0, right? In other words, we've just calculated that the normal vector field is straight up what? It's simply minus cosine t minus sine t. If we've done this calculation correctly, the normal vector field, right? I'm sorry, I'm forgetting my vectors on n and t. I don't mean to do that, guys. All right, if you see me do it, say something. All right, but so the normal vector field is that. Of course, it has to be that, right? Because it has to be a unit vector, right? There can't be any surviving r or square root of m squared plus r squared, right? It has to be a unit vector. That is a unit vector. Yeah? So actually, if you understand things well in terms of the vector analysis, you could have just written, like a lot of time, guys, I will just go straight from this to, this is really minus r not minus, but it's just r divided by the square root of r squared plus m squared, right? Times minus cosine t minus sine t 0. And you see, if I write this down, what I'm about to underline in green, once I have this, I notice that this is positive, right? Because, by the way, what did we assume last class? We assumed that r and m were positive, right? We're still doing that. Point of order. R, m greater than 0. I mean, technically speaking, we could allow m to be negative. That wouldn't change anything here. But definitely I want r positive. I'm thinking of it as sort of the radius of the helix. So this is a positive constant. This is a unit vector. That means that this has to be n. Because n is the unit vector that points in the dt dt direction. So yes, I can do the algebra and derive it, but I could also just like go directly from this calculation to there, which I will do other classes when I'm just calculating. Okay, so how do we find the binormal? Well, the binormal is t cross n. So we have to calculate the cross product of my t, which was, let me leave the constant out front, which was what? 1 over the square root of r squared plus m squared. And we've got ourselves a minus r sine t, r cos t, m cross product with minus cos t minus sine t, 0. So we calculate this cross product, and what's going to happen, we'll leave that constant out front because we can. All right. Now let's see here. So I get a m sine t for my first component. Z cross x, I get a minus m cosine t for my second component. And then for the third component, I get xy, so I get r sine squared t plus r cosine squared t. In other words, the binormal is 1 over the square root of r squared plus m squared, m sine t minus m cos t, r. So there's my n, there's my b, there's my t, right? This collectively, altogether, is called the Frenet frame. So the Frenet frame is T, N, B, like that. Now we can double check my work, right? Is the dot product of B and N 0? We get minus M sine cosine plus M sine cosine, 0, yay, 0, R times 0, 0. So yes, the dot product of N and B is 0. We also can see that n dot t is equal to 0 through explicit calculation here. And by construction, of course, n dot b is also equal to 0, right? My bad. N dot, what's the other one? N dot b, n dot t. Oh, b dot t, right? Yeah, b dot t. You can also see that that's 0. So these are mutually perpendicular, and they're set up so that the third one is the cross product of the first two. They're a right-handed frame. Now we can picture these three for the helix, and I think it's instructive, you know. So so here's my attempt at drawing the helix. So the unit tangent, to start with, it's horizontal like this. The unit normal it points like that. B points like this. We get over here, B still points, let's see here, N. So this is the interesting thing. The N one, it's always pointing like just towards the z-axis, basically. There's my N's, right? And the unit tangent, that's sort of into the board. This one's coming out at you, right? And the binormal T crossed into N, so it's kind of, I have a hard time drawing it, but you know, something like that. T crossed into N, something like this. So if you were to follow the helix, you could, you know, imagine the binormal, the normal, and the tangent, right? So here it is. If you can imagine this. So I'm starting, I point the tangent in the direction of the helix, right? And coming at you, it comes up and it goes around like that, right? But if I was doing this right, it's the normals. Notice the normals always horizontal. I'm not very good at holding these such that they keep the blue marker horizontal, but I should be doing that if I'm true to the math, right? Because the normal is always minus cosine minus sine, so it's like a horizontal vector pointing like. But you know, the B and the B also is always sort of the B's not vertical, right? It does have a an x and y component as well as it goes around. I think my picture's not quite right there because that's not quite right. The original binormal is not z hat, is it? When you put t equal to 0, what do you get? 0 minus m r, right? So it should be like originally, it's supposed to be slanting a little bit back like that, right? So because the basic problem with my picture to start with is the tangent isn't horizontal, it's actually pointing up a little bit, right? And the binormal points back a little bit at that point. It's leaning back in the negative y direction a bit. See, at time 0, the tangent is 0 rm. So it's like pointing in the positive y direction and up a little bit. All right. Okay, so that's the TN. Yes, sir.
So which vectors correlate to which color?
In my picture, I'm using, oh, fair enough. T for the tangent. I'm using green for the tangent in my picture. I'm using blue for the normal. And I'm using red for the binormal in this picture. I think I did that in my other picture over here too. Yeah. But I mean, fair enough. I didn't color code. My bad, you know. I should have done. If I was more at my game, guys, this would have been T, all right? You can't have a different color letter and vector symbol. That would just be wrong. I'm joking. Let's see here. This is N. And admittedly, this is B. All right. Yeah. Okay, so we've calculated the Frenet frame for the helix. And I mean, if that's all you could do, that would be interesting enough, but there's more. All right, there's much more. And so what I want to show to you is that we can, like I claimed that N and T were perpendicular, and you saw it's true for this particular example. I want to prove to you that it has to happen for any example. So how can we show that? So let's talk about the calculus of the TNB frame. that was sad. So first of all, notice that t dot t is equal to 1. Right? I regret putting vectors on the t, but it's too late. So t vector dot t vector is 1. It's a unit vector, right? What happens when we differentiate this? So we differentiate this product rule, right? So we've got dt dt dot t plus t dot dt dt equals to 0, which implies that t is perpendicular to dt dt, which implies that t is perpendicular to n, because n is simply a scalar multiple of dt dt by definition. All right? And there's nothing especially tangential about this calculation, right? We can go through the same calculation and see that n dot n equals to 1 and b dot b equals to 1 imply what? They imply that, n dot dn dt, right, is equal to 0, and b dot db dt is equal to 0. In other words, a unit vector field, if it changes, it cannot change in the direction in which it's pointing. It has to change its direction. It can't change its magnitude. Why can a unit vector field not change its magnitude? It's a unit vector field, so it has to stay length 1, right? So its only option is to change its direction. That's what this calculus is telling us directly. So this is one thing. Now, the TNB frame is a frame, right? So we can build any vector in terms of these particular unit vectors. So in particular, I can talk about the change in t with respect to time, right? And that I can calculate as, I'm going to use the prime notation, t prime dot t plus t prime dot n plus t prime dot b. What am I doing? Why can I do that? So what I'm doing here is using, like, you have x hat, y hat, z hat, right? That's a frame. I can build any vector from the vector components in the frame, right? Like, this is exactly akin to any vector v is like v dot x hat, right? Plus v dot y hat, plus v dot z hat, right? So think of x hat, y hat, and z hat being replaced by t, n, and b. See, because those are unit vectors in the right-handed sense. So everything I know about how to break a vector into pieces for x hat, y hat, z hat, it also works for t, n, and b. So if I want to study the change in the tangent vector, I can break it up into 3 pieces: the tangential piece, the normal piece, the binormal piece. And I can do the same thing for dn dt, you see. So I can do n prime dot t plus n prime dot n plus n prime dot b. And of course I can also calculate db dt in the same way. I can break it up into its components: its tangential component, its normal component, and of course its binormal component. But by the calculus that I have right above these equations, what do we know about these terms? Like, this is what? 0, this is 0, and this also 0. But what was our definition? What was our definition of n? Right, yeah, let's write that down over here. I miss the juice. All right, so our definition was that n vector is equal to 1 over the length of t prime, right, times t prime. So what does this tell us? This tells us that t prime is equal to n times the scalar multiple of the length of, like this, right? So what is t prime dot b equal to? Also 0. So n dot b is 0, right? N dot b is 0 because we remember our definition of b is t cross n, right? So by construction, b is perpendicular to n. So, yeah, you're right. That's also 0. All right? Huh. There's a way to show this is 0, but I forget. There's a way to show this is 0. This is 0. I forget how to show it at the moment, but we can show that's 0 as well. Let's see here. How could we maybe show that 0? Any ideas? How about this? We know that well, we know that n dot b is 0, right? So if we differentiate this, this tells me that n prime dot b plus n dot b prime is equal to 0, right? So this shows me that, I'm trying to get my pause on b prime dot n. So this shows me that b prime dot n is equal to minus n prime dot b. But what's n prime? It doesn't, I mean, yeah, this doesn't help me. I tried. All right, I tried. Didn't help. Man, Let's see if I have a helpful thing in the notes. I think it comes from looking at b being t cross n is where I found it from. So if you look up page 109, it's there I derive it. What's that? Yeah, page 109. In section 2.2. Like, yeah.
In your calculus with T and B, why do we have dt? Why do we have a plus two things equals 0 on the
Oh, well, last class we showed that the class before last, we showed that if we have the dot product of two functions of time, two vector functions of time, when we differentiate the dot product, we have a product rule. So the derivative of this product of functions of time, when differentiated, gives me dt dt dot d plus t dot dt dt. It's the product rule for the dot product.
So why don't we have that for N and B then?
Oh, I'm just skipping these steps, but it's the same. It's the same argument.
Oh.
Yeah. All right. Well. So this didn't help. This didn't help. If I take, let's try this. If b is equal to t cross n, right? So if I calculate db dt, that is, of course, dt dt cross n, right, plus t cross dn dt. But we already know that dt dt is just what? It's just, it's t prime dot n times n cross n. I'm using the calculation we've already done to simplify that. See that? I'm using this right here to put that there, all right? And then I've got plus t cross dn dt. What's dn dt? Well, dn dt has two pieces in principle, right? It's got n prime dot t times t plus what? Plus n prime dot b times b. So this is what, on page 109 I'm doing this, but I've introduced constants like labels, C12, C13, C23 and stuff. Those constants are playing the role that the dot products I have are here. Anyway, so my point is simply this. This is t, there's a vector here I've neglected to write. What's t cross t? What's any vector cross product itself is? 0, right? So this piece is gone, and we're just left with dB dt is equal to n prime dot b, right, times t Cartesian product, doesn't mean Cartesian product, cross product with b. What's t cross b? Is it?
Is it negative n?
It's negative n because of the right-handedness. So this is in fact minus n prime dot b times n. I keep going back to look for my eraser shirt because I just don't know what to do without it. Cool. So let me collect our winnings. All right. What have we got? We've shown that the derivatives of the normal and the tangent and the binormal, they have to be related to what? So you guys help me out. We've shown that dt dt has to be equal to, what's it? T prime dot n times n, all right. And we've shown that dn dt has to be equal to n prime dot t times t plus n prime dot b times b. And we've shown that b dt, right, has to be equal to what? B prime dot t times t. However, that's also equal to what? Do we have something else from that? dB dt is also, oh wait a minute, hold on a second, not t. I should have gotten an n there. Whoa. How did I get 0 here? Oh, this is wrong, right? Come back over here. This is what happens when I try to remember something rather than derive it. If we derive it, what's the derivation say? The derivation doesn't say that this is 0. This derivation says what? This implies that dB dt dot t is what? That's 0. Right? Because dB dt is only in the n direction. So that means that this piece is gone. And that, on the other hand, so this can either be written as b prime dot n, or, alternatively, minus n prime dot b. Those are equal as it happens. So, but it is in the n direction. Did I get it right now? b prime dot n, or n prime dot b, n. But there's a minus on the n prime dot b. All right. Okay, so let gamma tilde be the unit speed parameterization of the path. Then we say that dt tilde ds is equal to kappa times n, and dn tilde ds and db tilde ds. dB tilde ds is minus tau times n, and this guy is in fact minus kappa times t. I guess these are supposed to be tildes. I'm sorry, guys. Tilde, 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 tilde. Plus tau. And if you want to, you could probably put tildes on the kappa and the tau too. This is all. I'll add some tildes. Tildes for everyone. So here the tilde is just indicating that these are the quantities parameterized with respect to arc length. Yes, sir? I haven't defined it yet. So I'm saying define kappa tilde and tau tilde as such. Now I can give you a more precise definition. So like kappa tilde, which is a function of s, right, is equal to the magnitude of dt tilde ds. And tau tilde is equal to the magnitude of dB tilde ds. You asked what they were? That's a good question. Kappa is the curvature, and tau is the torsion. What I've just derived for you guys is that the differential equations that govern the time evolution of the Frenet frame are governed by the curvature and the torsion. Now, what's the relation between like unit speed and speed t? There's a simple chain rule, right? So like here's how it goes. If I have a vector field, let's say A for a second, which is function of, let's start with t. I can rewrite that as like ds dt times dA tilde ds in our notation. So in other words, the time derivative of a vector field is the speed times the unit speed derivative of the reparameterization of the vector field with respect to the arc length. But this also, on the flip side of this, we have that dA tilde ds, right, is 1 over the speed times the time derivative. So let's see here. So if I trade these for the unit speed derivatives, what does it look like? I get v, right, the speed, times d tilde, dt tilde ds. This is the speed times dn tilde ds. This is v times db tilde ds. And from this, then, you can see that on the flip side, these are equal to this here, and this here, and this here, right? So getting to the point, we find that dt dt is equal to kappa v times n, dn dt is equal to minus kappa v times t plus tau v times b. And finally, dB dt is equal to minus tau v times n. And these are what I would call the Furness-Ray equations. They define how the curve evolves in terms of its given curvature and torsion. In other words, I can kind of say the DNA of a curve is given by the curvature and the torsion. So the definition I gave right here is for the arc length parameterization. You see what happens over here is you can see that if you want to calculate the curvature as a function of time, we have to do what? Curvature as a function of time is going to be equal to like 1 over the speed times the magnitude of dt dt. All right, and the torsion as a function of time is 1 over the speed times the magnitude of dB dt. So, all right, so what I'm trying to tell you guys is there's two paths to go down in terms of calculating curvature and torsion. The one path is to reparameterize your curve with respect to arc length. Then you can straight up use the definitions here and here to calculate curvature and torsion. The other path, which I usually recommend, is that to calculate the curvature and torsion, we have to remember that we divide by the speed if the speed's not 1. Excuse me. You guys have given this to me already. You started me sniffling. And by the end of the lecture, now I'm sniffling. It's all your fault. I don't know who it was, but somebody in here, I heard you. I heard you. All right, anyway. So what is the curvature and torsion for the helix? Can we calculate it? I think I've got enough room right here to do that. So the point of the derivation we just did was to show you that that if we define the particular, values for the, t prime dot n and also n prime dot b, defining those two values fixes this whole thing. Like whatever I put here and here, it fills out the rest. So I just need to know those two functions, and it fills out everything. So if I just give names to those functions, namely curvature and torsion, then we can study the properties of curvature and torsion. The reason I jump back to arc length is because if I defined the curvature and torsion with respect to time, that begs a question like, how many different parameterizations are there for a curve? There's like infinitely many, right? So if I define curvature and torsion with respect to just an arbitrary parameter t, that begs certain questions of like, well, what if you chose a different t? So to avoid that, we simply make the definition in terms of the unit speed parameterization, which is unique given a choice of base point, right? There's only one arc length parameterization of a curve if you pick a starting point. So if we define curvature and torsion in light of the unit speed parameterization, then we have defined curvature and torsion geometrically, right? So the rest of this lecture, I'm going to try to explain to you what do these things mean geometrically, right? So first of all, let's calculate for the helix, all right? So the curvature, and I'm going to use the speed formulas because reparametrizing with respect to arc length gives me no joy. So kappa of t is 1 over the speed times the magnitude of dt dt, right? We calculated last time that the speed was 1 over the square root of r squared plus m squared. And what's the magnitude of dt dt? It's right here, isn't it? It's r divided by the square root of r squared plus m squared. So you see, the curvature for a helix is given by r divided by r squared plus m squared. V is speed, yeah. So kappa is r divided by r squared plus m squared. And I, you know, the funny thing here is the time dependence is kind of silly, right? The curvature is constant for a helix, at least the one we're studying. All right. How about torsion? If you don't mind, I'm going to erase a little bit here. So I've got B. I'm not going to erase that. I want to differentiate B. Oh man. How do you live like this? Anyway, let's see here. I love Dr. Sobrano. dB dt. Let's see, 1 over the square root, r squared plus m squared, yeah? Differentiating this gives us what? It gives us a m cos t. And this gives us a m sine t, apparently, yeah? Derivative of r, 0. Okay, so what's the length of dB dt? I'll actually write it out for once. That's just a really complicated way of writing m. So m over the square root of r squared plus m squared. Yes, sir?
When you differentiated b, did you? Why didn't we take the constant out front and keep it in addition to the 1 over b that was there? Or am I just?
Well, if I could do that, but then that would cost me dividing r by m.
I'm sorry. A little.
I can't. I mean, if I factor m out of here, I have to do it like this.
Well, sorry. I meant like we have the 1 over b is the 1 over the square root of r squared plus m squared.
Oh, you're saying up here. You could have just been like m over the square root of r squared plus m squared cos t sine t 0, and you can have been like, aha, unit vector. Therefore, magnitude. I totally agree.
I'm sorry. I think I'm not communicating as well, and also I'm confused.
I wanted that to be what you were saying. Oh well. All right.
I'm sorry, guys. But so like the 1 over b is the 1 over r squared plus m squared, and then when you differentiate b, isn't there another one of those that you have to multiply to? Oh my gosh.
I haven't gotten to the torsion yet.
No, yep. Never mind.
You're a step ahead. You're thinking of torsion. Now the torsion at time t is 1 over the speed times the magnitude of dB dt, which we just calculated. And you're right to be thinking about speed because there's kind of a copy of the speed right in there. So we have 1 over the square root